the colloquium series in 2021, and today I am happy to present Brian LeRoy, who is a professor at the University of Arizona, and he is one of the leaders in this new, recently established field of the twisted monolayer materials. Brian has made his PhD in Harvard University in 2003, and after the postdoctoral position at the Kavli Institute of Nanoscience in Delft, Netherlands, after that he has become a faculty at the University of Arizona, where he's professor now. Brian is an APS fellow and has an SF Area Award. So, okay, Brian, please feel to start, and we will enjoy the talk.
Hey, thank you, Dimitri. Thanks for the introduction, and thanks for the invitation to give this talk. So this is, I guess, one of the advantages of our current situation, being able to give talks anywhere around the world from your computer. So today I want to tell you a little bit about what my group does, and in particular, the work that we do on imaging local electronic properties of materials. So my group is focused on a range of different low-dimensional materials, trying to understand their electronic properties through imaging measurements. And so this is things like looking at carbon nanotubes here at the top with near-field scanning optical microscopes, looking at plasmons, so excitations in the nanotubes, looking at correlated states. So this is a superconductor imaging vortices in it in a heterostructure. We also do optical spectroscopy measurements to try to understand electronic properties through optical measurements. So this is looking at some graphene flakes, different optical properties of it. You can see different colors corresponding to different absorption levels in there. And what I'm going to tell you about today is about looking at local properties of two-dimensional materials. And so that's what my group has been focused on mostly for the last few years. And so I want to tell you some of the recent results that we've had in that area. So as I'm sure you know, the first 2D material that was sort of isolated was graphene. And so this was, I guess, now 17 years ago or so. And so this is, essentially a single honeycomb lattice of carbon atoms. So it's a monolayer thick material with these carbon atoms at each of the vertices in this hexagon. And so this was the first material that was discovered, but then fairly quickly after, there was a large range of other two-dimensional materials that have been isolated. And these materials all have sort of some things in common in that they have strong in-plane bonds, but then they have weak out-of-plane van der Waals bonds, which allows the materials to be exfoliated down to either single atomic unit cells or a few atomic unit cells. But beyond having sort of those characteristics together, they come in a wide range of different electronic properties. And so that starts with the graphene, which is a semi-metal, but you can also have things like molybdenum disulfide here, which is a semiconductor. And so this is a 3-atom thick unit cell with molybdenum in the center, sulfur atoms on the top and bottom. There are metal versions of this, things like niobium diselenide here, niobium sulfide. These are materials which are essentially metals. At room temperature, if you cool them down low enough, they undergo a transition, in the case of niobium diselenide, around 7 degrees Kelvin to a superconducting state. And then sort of to fill out the different properties here, we also have insulating materials, things like hexagonal boron nitride. We have the same structure that you have in the graphene, so a single atomic layer of material, but instead of having carbon atoms, you have alternating boron and nitrogen atoms. And so this boron and nitrogen, this alternation breaks the symmetry in the crystal, and instead of being a metal, then you have a large band gap, 5-6 eV in this material. And you also have naturally occurring things like mica, which have the same sort of general properties, where you can easily separate the layers because of the weak van der Waals bonding. And so what was discovered is you go to these other two-dimensional materials, you can enable a wide range of other electronic properties that you don't have necessarily in graphene by itself. So graphene, being a metal, is hard to make high quality transistors. If you use something like a semiconductor, this molybdenum disulfide, you can see a large on-off ratio in this transistor, something like 10 to the 7 or 10 to the 8 ratio between the on and off currents. In all of these two-dimensional materials, because they're just a single atom or a few atoms thick, you can make things like flexible electronics if you pattern them onto plastic or other sort of flexible substrates. The semiconductors also have photoluminescence, so they can give off light at certain wavelengths here or absorb light at certain wavelengths. And then you can imagine from that making things like solar cells, which are sensitive to wide ranges of different energies, instead of silicon, which is sensitive to just a single wavelength. If you combine these materials, you can get a multi-junction type solar cell and be sensitive to a wider range of wavelengths of light. And so that's one of the ideas that we're going to use here, is to try to combine these materials and to enable new or different functionality. And so everything I'm going to talk about today is going to be made with these two-dimensional materials, just using very simple mechanical exfoliation techniques. And so what we're going to do is we're going to essentially use Scotch tape, place the crystals on there, put the tape together, peel it apart, thin it down, and eventually get a large smearing of the material on the tape, and then press it onto a silicon oxide substrate. And when we do this, we'll leave behind on the substrate some thin layers of material, and then we will look for these in an optical microscope. And so what we do then, when we're doing this visualization, is just by the color of the material, we can learn something about the thickness of it. And this is from a thin film interference effect. By picking a suitable substrate, this silicon oxide, this glass, on a reflective silicon substrate, we can be sensitive to different thicknesses of the two-dimensional material that we put on top. And so what you see in the top corner here, this is actually a graphene sample, which is grown by chemical vapor deposition, but it highlights nicely the different colors. The gray background, the light gray you see, is just the bare silicon oxide. And then you see in this region, a monolayer of graphene, a second layer here, a third layer getting a little bit darker, and a fourth layer in the middle. And so just very simply from an optical microscope, we can determine the number of layers of our two-dimensional material. If you look on the bottom right down here, you can see the same thing in a color image instead of black and white for graphene. The orange is the silicon oxide, a monolayer, bilayer, 3 and 4 layers, etc. And we can do the same thing with the other materials that we're going to be interested in: hexagonal boron nitride, molybdenum disulfide, etc. And so we have a very quick and easy way of determining how many layers of the material we have, which will be important as we try to make different heterostructures with these materials. And so the idea that I want to sort of get through in this talk is that by taking these relatively simple materials, you know, a metal like graphene, or an insulator like hexagonal boron nitride, a semiconductor like the molybdenum or tungsten, sulfide and selenide materials, by combining them, we can enable very different and unusual functionality in the materials, stuff that we cannot have in just a single monolayer. So I'm going to talk today and give some different examples of how combining these materials leads to new functionality. And so the first thing we need to do is actually have a way of designing these stacks and being able to create these heterostructures. And so we do that through a micromanipulation process and a sort of a dry polymer stamping technique. And so what you see here is a stage. We have a stamp on it, which is controlled on a 3-axis micromanipulator here. And if you go and look at this stamp up close, what you'll see is it's a glass slide. And on top of that, there's a little PDMS sort of bubble, and that's covered in a polymer film, in this case, polycarbonate. And so that's going to be what the material that we use to stamp and pick up our flakes. And so we have this stamp upside down. We put our flake that we're interested in underneath. And in this case, let's say it's a tungsten selenide flake. We have the stamp, we put it on top, and we bring these into mechanical contact. So we essentially just lower the glass slide into contact with the silicon oxide, and then we heat the stage up to about 60 to 90 degrees Celsius. When we do that, this polycarbonate slightly melts, and that then picks up the tungsten selenide off the silicon oxide substrate. So we pick up the flake onto the stamp, and then we can repeat the process with another flake and another flake, and however many flakes we need to make our heterostructure, we continue to do that to create the entire stack. And so we create this heterostructure stack up here on the stamp, and then we eventually go and have our target substrate. Maybe we have some gold contacts on it, and we bring this down into contact. Now we heat to a much higher temperature, 180 degrees Celsius. That's hot enough to actually melt this polycarbonate. And so instead of picking up the sample, we actually melt the heterostructure stack down onto the substrate underneath, and then it's patterned onto this substrate. And so here's a couple images of different heterostructures that we can form. And what you'll see here is each of the different colors is different layers. So in this case, we have something like graphite in the background, different boron nitride insulating layers. There's a tungsten selenide, molybdenum diselenide heterostructure in the middle here. Other ones here, you can see graphene sticking out here, boron nitride, and some other layers in the middle here. And so we can make essentially any arbitrary stack that we want just by picking these up and continuing to do that until we have the complete structure built, and then we melt it down. And once we've done that, we can pattern electrical contacts, as you can see in this top image here, these gold contacts to it, or we can place it directly on those metal contacts. And then what we want to do is we want to actually go and probe the properties of this heterostructure that we've created. And so the way that I'm going to do that for, I think, all the measurements in this talk, or almost all of the measurements in this talk, is with low temperature scanning tunneling microscopy. So this is an example of a STM that we have in the lab. It's operating at 4.5 Kelvin in ultra high vacuum. So that gives us very good stability. So we can stay over a region for a long period of time. The low temperature gives us very good energy resolution so that we can essentially see things that are occurring on the sort of millivolt, millielectron volt scale. And the trick here that we need to do is that this previous slide here, you can see these scale bars. These devices are generally on the order of 5 to 10 microns in size. And so we need to position our tip onto the sample here with about a 5 micron precision. So we need to actually land the tip directly on the sample on the active region that we're looking to investigate. And so we have some optics on the outside of here looking in here so we can actually visualize where the tip is landing on the sample and be able to perform the measurements at our desired location on the sample. So let me just quickly spend 2 slides here reviewing scanning tunneling microscopy, mostly to just sort of show you and remind you the types of measurements you're going to see throughout the rest of the talk. And so the STM can operate in 2 different modes. The first mode is a topographic mode. So in this mode, we are using a tunnel current with a feedback circuit where we keep this tunnel current fixed, and we're scanning over the sample. So we have our sample, we have our tip, and we're scanning over, keeping the tunnel current fixed. Because the tunnel current is exponentially sensitive to the separation Z between the tip and the sample, that gives us a very high resolution image of the atomic structure in the sample. So this image down here is an example of a graphene on silicon oxide substrate. You can see there's lots of corrugation, and then if you look closely, there are hexagons here corresponding to this honeycomb lattice of the graphene. In addition to this exponential sensitivity of the current with the separation, there's also this integral here over the density of states. So this topography measurement measures from the Fermi energy up to our bias voltage, the integrated density of states. And so we can take advantage of that. Instead of scanning and having our feedback circuit on, keeping a constant height, we move the tip to a fixed location. We turn off the feedback circuit and we change this bias voltage, this voltage between the tip and the sample. And when we do that, if we now measure the change in this current with this bias voltage, that gives us a derivative of this integral, which will then give us something proportional to the local density of states at the current position of the tip. And so this is an example of type of measurement you'll see here, di dv. So this is proportional to the density of states as a function of the voltage on the tip, or the voltage between the tip and the sample. And what you'll see here, this is for a graphene. At the Fermi energy, graphene has a very low density of states, so this goes near zero. As you go higher in either the conduction or the valence band, the density of states increases, and in graphene's case, it increases linearly with voltage. So those are the two main modes that we can use for the scanning tunneling microscope. There's a third operation that we can use, which is to basically combine these two modes together, is to take topographic measurements at the same time as we're taking local density of states measurements. So in this case, we can essentially combine these two and look at how the local density of states is varying with position in the sample. And what you'll see here, this is about a 30 nanometer scan here of the topography. We can go zoom in on there and we'll see something corresponding to the atomic lattice of the graphene. If you zoom in on the local density of states in the same area, being acquired at the same time in this case, this pattern you see in the local density of states is actually different than the pattern you see in the topography. If you were to look at this carefully or do a Fourier transform of this data, you would find that the wavelengths that are appearing in this local density of states are different than the wavelengths that are appearing in the topography. They're a factor of square root of 3 longer. And they're coming from the fact that the electrons in the graphene in this sort of disordered sample are undergoing a lot of scattering, and that scattering is in certain preferential directions. And so from this measurement of the local density of states, we can learn something about the scattering or the disorder in the sample. And so by combining these topography and local density of states measurements, we can get more detail and learn more about the underlying wave functions in the sample. So those are the types of measurements that we're going to talk about and show you today. And so what I want to do during the rest of the talk here is to try to talk about 4 different types of measurements. And what they all have in common is that we're going to enable new functionality by using the twist angle between the materials. So we're going to control not only which materials we stack together, but also the orientation, the relative orientation between the different materials, and see how that can affect the functionality of the heterostructure. So I'm going to first talk about what happens when you put just graphene on a simple insulator. What happens as you control the twist between the graphene and the insulating material. Then I'll talk about putting graphene on itself. So graphene on graphene, and in 2 different types, 2 different regimes here. One, this one in the top right is very small twist angle. So make just a tiny rotation between them, and how does that affect the band structure of the graphene? And in this other case, the so-called magic angle graphene, when you make about a 1 degree twist angle between them, and you can induce superconducting and correlated insulating states in the graphene. And then at the end, hopefully there'll be time to tell you a little bit about what happens when you combine, in this case, tungsten selenide on top of each itself, 2 different layers of tungsten selenide, and rotate them, and how that can modify the electronic properties of that material. So first, I'll talk about graphene on insulator, but before doing that, I guess I will pause and ask if there are any questions before I move into that.
Okay, I think we have a question from Alex. Would you like to ask it?
Hi, yeah, just a quick question. When you're doing the assembly of the stack layers, how do you get rid of all the residue from the PC?
Yeah, so there are a couple different ways that we can get rid of the residues. So the first way is we vacuum anneal the devices. So the residue ends up only being on the top of the first layer, because the PC comes in contact with the first piece that we pick up, and then every piece that we pick up subsequently is only coming in contact with the previous one. So only the top one comes in contact with the PC. So when we're done making the stack, we can just vacuum anneal that and get rid of the residue there. A lot of times what we actually end up doing is flipping the entire heterostructure over after making it, and that puts the PC underneath everything. And so then when we're probing on the top with our STM, we're not going to be sensitive to that residue. But which of those two processes we do depends on which heterostructure we're going to make and what order of layers we need to pick up, and etc. But we can do either of those to remove the residue.
Okay. I have also a question. These expressions for the tunnel current, they assume that the density of states for a tip is constant. How
Correct.
good is this approximation?
It's pretty good. So we always check the tip on a gold substrate to make sure that we don't see any variation in its density of states. The approximation obviously breaks down if you're gonna try to do measurements over a very large voltage range, right? The approximation also assumes that like the tunneling matrix element is energy independent and these sorts of things. But generally we're interested in looking at changes over small energy ranges, and in that case the density of states of the tip is generally pretty constant.
Okay. Thank you. Do we have any other questions?
I have two sort of questions, if that's all right.
Of course.
Is my mic working very well? I can't tell.
Yes.
Yep. Okay, cool.
I think we hear you.
All right. First one is obviously with this mechanical exfoliation, there's sort of like limiting steps. Did you find that the area size was more limited by the initial layer that you would put down in these mechanical exfoliations, or did it get progressively harder with each layer because of adherence, etc.?
No, it's essentially limited by the size of the initial flakes that you can find. Depending on, some things like graphene are easy to find large flakes. Things like tungsten diselenide, the students have a much harder time finding large flakes. And that's the limiting steps or limit for that range.
Okay, so did you cater your base layer based off of that, or was it based off of like band structure calculations on what should go at the bottom?
Yeah, so unfortunately what the layers need to be is dictated by the physics of what we're interested in studying, and so we're at the mercy of that in terms of which materials that we end up with on the top layer versus the bottom layer.
Yeah. All right, thank you.
Yep.
We have another question from Fixang. Sorry if I pronounced your name incorrectly.
Yes.
Let's go forward.
Can I ask the Moiré pattern you show here can be imaged by the topography mode, or only just by the local density of states?
I will come to that in the different sections. The different ones are, some can be in topography and some are in local density of states. So it depends on the material.
Okay.
But
okay.
I'll come to that as I talk about the different ones.
Oh, okay, thanks.
Yeah.
Okay. If you don't have any other questions, let's go ahead.
All right, so the initial sort of measurements of graphene back in 2004, 2005 was putting graphene on a silicon oxide substrate. And so when you do this, because the silicon oxide is an amorphous material, there's not really any sense of twist angle matching between them. You have the crystal structure of the graphene, and you have this amorphous silicon oxide substrate. And so when you do these measurements, you don't see anything particularly interesting as you change the rotation or change the alignment of the graphene on silicon oxide. But about 10 years ago now, that started to change when you started putting graphene on other crystalline insulating materials. And so in particular, the first one was putting graphene on hexagonal boron nitride. And so this material, as I already mentioned, has a lattice structure which is identical to graphene. And it actually has a lattice constant which is fairly close to graphene. There's about a 1.8% lattice mismatch between them. And so now you actually have two atomically smooth surfaces that you can put together in these heterostructures. And so that's what we're going to use as our first way of taking advantage of matching these materials on top of each other. Boron nitride also has other nice properties for graphene in the fact that it's an insulating material. It doesn't really have dangling bonds or charge traps, and so you get a much higher quality graphene when you put it on hexagonal boron nitride than when you put it on silicon oxide. And so to sort of investigate that, we're going to look at the density of states of the graphene as a function of position on a sample. And so what we can do is, as I showed you before, these density of states, DI/DV maps, we can take them at different positions on the sample. Every place you do this measurement, you get this V from the density of states of graphene. The minimum point here corresponds to the Dirac point of the graphene conduction and valence band. And so you'll see here at this location, the Fermi energy is in the conduction band. So we're a little bit N-doped. Over here, we're neutral. Over here, we're P-doped. And so the doping changes as a function of position, and we can investigate that just with the STM by taking these measurements at different locations in the sample. And so what you see when you put graphene on different substrates is a huge variation in these disorder that occurs, or this variation in doping in the sample. So graphene on silicon oxide here on the left, you have potential fluctuations on the order of about 100 millielectron volts. You put graphene on the boron nitride, it gets significantly reduced. We're down here in the sort of 5 to 10 millielectron volt range, but you can still see a little bit of blue here, so hole doping, a little bit of red for electron doping up here. If you make a slightly fancier heterostructure where you put graphene, then boron nitride, then graphite, then silicon oxide, you see a perfectly white structure here, meaning that there's essentially no charge potential fluctuations in this sample. And the reason that's occurring is this graphite layer is a metal or a semi-metal. It's screening out any of the impurities which are in the silicon oxide, the HBN that is acting as a nice insulator, and your graphene on top is giving you then a high quality graphene to look at. And so these are the types of structures that we want to use now to probe interesting physics occurring here in the graphene. So we've got structures, so we get rid of the disorder from the substrate, and now we can start looking at what happens to this graphene on different materials, in this case, looking at the graphene on hexagonal boron nitride. And so these are fairly large scale images. These are something like maybe 80 nanometers across. If we go and look more closely, what we're going to see is Moiré patterns arise because of the mismatch in the lattice constants of the two materials. So we have our hexagonal boron nitride in white and our graphene in yellow, and we're going to put them on top of each other. And so if you see, if I combine these with about a 5-degree twist angle between them, I get this Moiré pattern here where it's a periodic structure with a periodicity of something a few times longer than the atomic lattice. If I rotate the graphene by 5 more degrees, so now I have a 10-degree rotation between these, now I see this Moiré pattern here shrinking in size. And so just as I rotate the graphene and the boron nitride with respect to each other, I get a range of different Moiré patterns. I'm not sure how well this animation will go through the zoom here, but if I take these and rotate them all the way around, what you'll see is that at every 60 degrees here, as I go around, I all of a sudden get to a very long wavelength Moiré, and then it shortens and gets very short now, and then starts to elongate. And then this repeats every 30 degrees as I twist these two materials on top of each other. And that's because they have this lattice mismatch between them of 1.8%. And so depending on the rotation I make them, we get either shorter or longer Moiré patterns arising. And it's fairly straightforward to calculate what is this Moiré wavelength, so this distance where this lattice repeats. It depends on just a couple parameters. One is delta, which is the lattice mismatch between the two layers. So in this case, 1.8% for the boron nitride and the graphene. Phi is the rotation angle between the two materials. And A is the lattice constant of the graphene. So when you put these numbers in, what you'll see here is that the wavelength as a function of twist angle has a maximum of about 14 nanometers when you put in phi of 0 here, coming just from the lattice mismatch between the two materials, and it shrinks down as you make the materials more and more twisted from each other. And so what you'll see in the bottom here is different topography images. So these are all coming just in the topography at 2.4, 6, and 11.5 nanometers. And you can see in the different cases, the Moiré pattern that forms as we twist the graphene to different rotation angles here. So this is what happens to the topography of the sample. This Moiré pattern, though, is also a electrostatic potential for the electrons in the graphene. So it also will affect its density of states. And so we can see that effect of the density of states by looking at the dIdV as a function of energy. And so what this color scale map is showing here is the density of states. Here's the color scale as a function of voltage on the y-axis between the tip and the sample. And the x-axis here is the gate voltage, or the doping level in the graphene. And what you'll notice is there's this blue dark point that runs along here, kind of in this pattern like this. That's coming from the Dirac point in the graphene, so that's our minimum in our density of states. And there's a second dip that's running completely parallel to it along the bottom here. And this is coming from this periodic potential. So from this superlattice that's created by this long wavelength potential that is modifying the graphene density of states and creating a whole new set of superlattice Dirac points, in this case, about 300 millielectron volts below the Dirac point. And so this is one for, I think it was a 9 nanometer Moiré pattern. As you change the twist angle, you change the wavelength of the Moiré, as I showed you on the previous slide, and that changes then the energy of this superlattice Dirac point. So even though this boron nitride is a wide bandgap insulator, something like 5 or 6 electron volts, because you can play with the twist angle between the graphene and the boron nitride, you can modify the electronic properties of the graphene, and in this case, induce new superlattice Dirac points at a controlled energy just with the twist angle between the materials. So I guess I'll pause again. I think maybe there were a couple of questions in the chat before I go on and talk about what happens when you put graphene on itself.
Yeah, we have, I think, 2 questions from Alex.
Sorry to keep hassling you. So that's
no problem.
Really nice. So do you have a feel for, I mean, the improvement with the HBN and then the graphite is dramatic in terms of the residual disorder that's left. Do you have a feel for how much disorder is left once you've put the metal screening and the HBN in? Yeah.
It was essentially below our detection limit. So, you know, we have an energy resolution because we're at 4 Kelvin of about 1 millielectron volt. And so it is below the level of 1 millielectron volt So it's at least 2 orders of magnitude reduced from what you see on graphene on silicon oxide. But I can't really say if it's 100 micro EV, 10 micro EV. That's below what we can detect.
So in terms of carrier density, it's below 310 to the 10, roughly.
It's something, yeah, low 10 to the 10s, yes.
Right. Okay. Great. Thanks.
Yep.
Okay, I also have a question. So in graphene, the spectrum is almost almost perfect electron hole symmetry.
Yes.
But for this twisted system, the plot you have just presented, it's definitely very well broken. So, there is another Dirac points below at valence band? I mean, could you show the sketch again? Yeah, so you have Dirac point at the top.
Yeah.
Do you have another Dirac point at the bottom where?
No. So this band would just grow going down here. I mean, so in principle, there's another set of superlattice Dirac points in the conduction band.
Oh, I see.
Which are the sort of electron version of these superlattice Dirac points. Except they are generally, I mean, you don't see them here in the data, and they're generally much weaker. And the electron hole symmetry is being broken in this case because we're coupled to the boron nitride substrate. And so the boron and nitrogen, the difference of those 2 atoms breaks this sort of electron hole symmetry that you have in the graphene, and preferentially gives you these superlattice Dirac points in the down here on the hole side.
Okay. I have another question. So the spectrum in graphene, the spectrum is gapless because you have the symmetry between 2 sublattices. So
Yes.
when you place on this substrate, locally it is distorted. So you have some energy asymmetry between A and B sublattices in graphene. So one could expect to have a gap open at the Dirac point, at least, I don't know, locally.
Yeah,
Why
and you do.
This
There
doesn't work.
No, there is a gap that opens here at the Dirac point. It's relatively small, on the order of 10 MeV or so, but there is a gap that opens at the Dirac point, as well as at these superlattice Dirac points. They're generally smaller.
Oh, I see. Okay, thank you. I think we have another question from Alex.
So one last question. How
Yeah.
uniform is the Moiré across the sample? Is there a domain size?
So in this graphene on boron nitride, it's pretty darn uniform. Occasionally you'll see like a wrinkle in the graphene or something, but for the most part, it's uniform. The next part I'm going to talk about is definitely not that way. When you put graphene on another sheet of graphene, but the graphene on HBN makes very nice Moiré patterns.
Okay, thanks.
Yeah.
Thank you. Okay, let's go forward.
All right. So now I want to talk about what happens when instead of combining a graphene with a nice insulator, you combine graphene with itself. So here we're going to take 2 of these same lattices and put them on top of each other with a controllable twist angle between them. And so if we're thinking in real space, we'll get these nice Moiré patterns that we just saw in the graphene on boron nitride. If you're thinking in momentum space, you have the Dirac cone from one layer, the Dirac cone from the second layer, and the twist is controlling the separation in momentum space of these 2 Dirac cones. And so by controlling the twist angle between them, we can move these cones either closer to each other or further apart. And this is then going to change the electronic and optical properties. And so to do this, though, you need a very good way of controlling this twist angle here, because in this case, it's going to be extremely sensitive to the twist angle between the layers. And so to be able to do this, we developed a technique to make very high precision, rotationally controlled heterostructures. And the way that this works, at least sort of schematically, is we take a piece of graphene here, relatively large piece, and we bring our PDMS PC stamp down, and we contact just 1/2 of it. So we make sure that we only touch down on 1/2 of it, and then we tear that part off. So we essentially tear along this white line, and we pick up only this top half of the graphene. And so then we have this graphene on our stamp. Then we take the substrate that's underneath, we rotate it by a controlled amount, say 1 degree, 2 degrees, 0.1 degrees. And then we bring our stamp over and we pick up the second half of this graphene. And since these two pieces of our heterostructure came from the same original crystal, we know that they were originally crystallographically aligned, and now we have a small twist between them that we have controlled just by the rotation of the substrate underneath. And so this allows us to make basically any arbitrary rotation we want between the materials. And so for graphene, on graphene, this is important because this equation I gave you for the wavelength as a function of twist angle has a divergence when the twist angle goes to 0, because delta is 0, they're identical lattices. And so it simplifies to basically the lattice constant divided by 2 times sine of the angle between them over 2. And so instead of having only up to 14 nanometer Moiré patterns, we can effectively get an infinite size Moiré pattern by making very small twist angles between the layers. And so here you see ones on the order of, say, 5 nanometers, maybe 30 nanometers here. Here's 50 nanometers. We've seen up to several hundred nanometers for these Moiré patterns. And so this means we're getting to very small twist angles here if you're reaching wavelengths of 50 nanometers. And so again, here's the same thing that I showed on the graphene on boron nitride. But now instead of having the Moiré pattern kind of twist as you rotate the layers, it just kind of comes in and out of focus and goes to this infinite wavelength for small twist angles. What this means in terms of electronic properties is that the graphene has different stacking arrangements at different locations in real space. So in some areas, the graphene sits directly on top of each other in this sort of AA stacking regime, where the carbon atoms of one layer are directly over the carbon atoms in the bottom layer. Other regions, we have AB stacking, the usual Bernal stacked graphene, or BA, the opposite version. And if you look at the density of states, or the energy versus momentum relation for these different regions, in AB and BA stacked graphene, you have a quadratic band structure, quadratic dispersion, whereas in this AA stacked, you have a linear dispersion. Now, if I apply an electric field in the Z direction, so in the vertically here, that's going to break the inversion symmetry in these crystals. And that means that in this AB or BA case, it's going to open a band gap and the graphene is going to become insulating. Whereas in the AA type regions, since we have these linear relations, it's going to continue to stay conducting. And what this means is we can play around with the electric field configuration to make sort of interesting topologically protected states in this structure. So imagine you have a Bernal stacked AB type graphene, and we can modulate our electric field from in plane to out, so vertically up to vertically down. Well, somewhere in the middle, the electric field has to go to 0. And so that means that we have band gaps on either side. At the 0 line, it would be conducting. But equivalently, instead of modulating the electric field, what we can do is we can use a uniform electric field, but modulate the stacking configuration of the graphene. So from this AB stacking to this BA type stacking, in the middle, we have to switch between them. In those regions, the graphene will remain conducting. It'll be insulating on both the AB and the BA side. And so there's been theory from about 10 years or 8 years ago now of what should happen here. And what should occur then is in the bulk of the sample where you have this AB or BA type stacking, the sample should become gapped, and the size of the gap is controlled by the magnitude of this electric field. And then running along the boundaries should be topologically protected conducting states. Here, 2 of them or 4 of them with spin going on each valley. When we look at very small twist angle samples, so in this case, a 0.25 degree twist angle, so this is a Moiré pattern on the order of about 100 nanometers. What you'll see here is these bright regions are the AA stacked regions. We have alternating AB, BA going around that, and then we have a domain wall separating the BA and the AB regions. If we now go and look at the density of states in this structure, we can look at the 3 different regions, the AB region, the AA region, and the domain wall. What you'll notice is as I apply an electric field, that's this backgate voltage as a function here of tip sample voltage. The color scale again is density of states. So dark means it's insulating, white means it's highly conducting. In the AB regions, when I go to high backgate voltage, it means I'm applying an electric field, and you start to see a band gap opening here. Right? There's this region of 0 density of states, and so we have a gap opening in the AB region. The AA region has all kinds of states running through it. It's a rather complicated pattern. I'll come back to this in the next section of the talk. But if we look on the domain wall, you see there's some states here at higher energy, but there's no band gap that's opening in the domain wall. There's a little bit here that's darker, but it stays relatively constant as I apply the backgate voltage or apply the electric field. And so what we can do is we can go and measure now spatially the density of states. If we go outside the band gap, so we go to energies above the band gap in the material, what you'll see is we have a fairly uniform density of states in the sample. The dark regions here are the AA sites where some interesting physics is happening. But in the rest of the sample, we have basically a uniform density of states, uniform conduction in the sample. If instead we go to an energy which is inside the band gap, so we lower our energy, we're inside the band gap. Now we have these dark regions, these dark triangles where the density of states is low. And so these are the A, B, and BA regions which are gapped. And around each of them, there are these 2 bright lines. These are our topologically protected states that are connecting the AA sites. So they're running along the domain walls, and they are topologically protected from this fact that the stacking configuration is changing from AB in this triangle to BA in this triangle, and along the domain wall there appears these topological states once the AB and BA regions become gapped. All right, so the next section I want to tell you about is what happens not when you make a 0.25 degree, but instead when you go to about a 1 degree, this so-called magic angle graphene. And so in this case, what you see happening is that the band structure of the graphene, you've brought the cones to just a magic distance apart, and that leads to a flat band in momentum space. So you have this 13 nanometer Moiré pattern that develops here. And what you see in the density of states here, right at the Fermi energy, you have this blue band, which is very flat, has almost 0 dispersion as a function of momentum. If you go to larger twist angles, you see still this sort of Dirac cone showing up here. If you go to the smaller twist angles, you have a very complicated set of bands here at low energy. But right at this magic angle, you get this nice flat band. And so this was first seen by Pablo Herrero's group at MIT in 2018, where they discovered superconductivity in these samples and correlated insulating behavior. And so as you change the charge density in the sample, when you completely fill the bands, you put 4 electrons or 4 holes in them, you get insulating states. At half filling, you also start to develop insulating states. And right around near those states, it becomes superconducting. This is some later work showing the same type of things. It's a very complicated phase diagram where you have superconducting regions, band insulators, correlated states, all being controlled here by just changing the charge density in the sample. And so these are done through transport measurements. So what we're interested in looking at is what's happening locally in these heterostructures as you change the charge density. And so the first thing we can do is we can just start with a simple topography measurement to just look at what the topographically what is happening in the Moiré pattern here. And so what you'll see here is that there are bright regions here and separated with dark regions around here. I think these labels all got shifted a little. The bright regions should be AA. This is AB here, and this is BA. And so what you'll see here on the schematic, right, the AA, it's surrounded by BA and AB regions going around. And so from this topography image, by measuring the separation between the AA regions, the different lattices, L1, L2, L3, we can determine the twist angle of the sample, and we can see that we're right at this magic angle of 1.1 degrees. There's also a little bit of strain between the different directions, so they're slightly different lengths. And so we have some strain in the sample, about 0.17%. And so someone asked earlier about the disorder in these Moiré patterns. Here, these are very sensitive to disorder. As you move through the sample, you'll often see this angle change from, say, 1 degree, 1.1, 1.2, et cetera. And you'll also see strain can develop. And that's coming from how these structures are made by tearing this graphene and putting it on top of each other. And so these types of moirés are much more sensitive to twist angle variations and strain than you see on the graphene on boron nitride. So that's what the topography looks like. Now let's go and look at the spectroscopy at these 2 different regions. So if we go to the AB region, so the area here, the dark regions on the sample, the density of states is pretty much flat. There's not much interesting happening. That's this green line here. Instead, if we go on this bright region here, that's the AA site, you'll see that there's these 2 strong peaks here. And that's coming from the fact that we are developing these flat bands. So they have a very high density of states. There's 2 of them. One we call this, say, the upper band and a lower band. And so that's these 2 peaks that we see are corresponding to these 2 bands in there. We can then investigate what happens now if we change the charge density in the sample. So the previous image that I showed you was a vertical cut through this data. So the axis here is the bias voltage, the tip sample bias voltage. The x-axis is the gate voltage, so we're controlling the charge density. And so you can see there's these 2 bands here, these 2 bright spots, and they're moving through in a very complicated pattern as we change the charge density. So they come down here, one goes like this, does a whole bunch of interesting things here, and then moves down this way. The other one comes down, goes further below, and then tracks down here. And so we're interested in trying to track what happens to these and understand what's happening to the wave functions of the electrons here as we go through these different charge states in our sample. So the first thing to look at is let's just look at the separation between these 2 bands. So these are the 2 bands here and here. So the first thing you can see is at the red point here, they're both above the Fermi level. So the Fermi level is 0. They're both above. So they are completely empty. They're fully depleted. There's no electrons in them. And they're relatively close together in energy. If we come here to this, where this white line is, what you'll see is that they are much wider. They're much further apart in energy. And this corresponds actually to the charge neutrality point. So the charge neutrality point here, we have exactly filled one band here on the left, and we have a second band which is completely empty. And so what happens is that as we've gone from fully depleted to the charge neutrality, the interactions have opened, pushed these bands apart and opened a gap here of something on the order of 25 or 30 MeV between them. Now, this is very sensitive to twist angle. So we can look at the ratio between how broad they get at neutrality versus how narrow they are when they're depleted. That's this ratio here as a function of twist angle. And so if you go to high twist angle, basically that ratio is 1. Nothing happens. That tells us that interactions are not important in that system. But as you go to this magic angle, right around 1.1 degrees, there's a factor of about 3 enhancement of the width. So that tells us that these are strongly interacting. There's strong correlations here right around this magic angle of 1.1 degrees. To look at this a little bit more detail, we can actually track how wide each of these bands are. And that tells us how flat the bands are. So the smaller the bandwidth, the narrower the band is, the flatter it is. And so you can see here that the bands themselves are quite flat. And then the white one is telling us how strong the interactions are. So the fact that the white one is very much enhanced in this region tells us the interactions are strong. The bands themselves are quite narrow, but they have some oscillations here as they get filled, as they have 1, 2, 3, 4 electrons in them. There's oscillations in their width as the interactions change. And so that's essentially what you see happening here is we're going through this band filling, starting here at this -4 state on the left. Both bands have 0 electrons in them, so they're both fully empty. When we hit this charge neutrality point, we have 4 electrons in the lower band. The upper band is completely empty. That's the white. Here, when we hit the purple, we've put 1 electron in the upper band. The lower band stays filled. At that point, there's a change in the width of the upper band because now there's an electron in it. As we put a second one in, we have another, it gets narrower, and then back up. Third one, it gets narrow, etc. as we fill these bands. To sort of connect these measurements with their transport measurements that I showed before, what we need to do is actually not look vertical cuts through here, but take a horizontal cut through this data. And that's telling us what's happening actually at the Fermi level. We want to look at what's the density of states at the Fermi level, because that's what's measured by a transport measurement through one of these devices. So if we take a horizontal cut through here, that's this white trace here. And what you'll see here, the red area that's was on the far left, the negative gate voltage, there's very low density of states. That's because we're in this insulating state. And we have this large gap here, very insulating region. At the white one, this is the charge neutrality. Again, we have a band gap there. It's not as wide as the band gap when we're fully filling the band, but there is an interaction-induced gap there. When you go to nu equals 1, you put 1 electron, there's a small dip here. Nu equals 2, there's a small dip. We don't see much happening at nu equals 3. When you get to nu equals 4, you fill the band again, and now once again you have a band gap developing there with these states now fully filled. And so we see the same sort of qualitative behavior to what you see in the transport measurements. Unfortunately for us, our measurements are about 5 degrees Kelvin, and these devices don't become superconducting until you get down to the regions of 1 or 2, maybe 3 degrees Kelvin. So we can't actually see the superconductivity develop in them, but we see the sort of correlated states, the correlated insulating states, and what are the precursors to the superconductivity in them. But the STM, what it does give us the power to do is to look at the sort of local density of states and how that varies in the sample. And so what we've done is we've taken maps of the local density of states as a function of the filling of these bands, and we want to look at how do their symmetries vary as a function of the filling of the bands. And so on the left here is a typical local density of states image. And then you can see we're going to just take one unit cell of it and plot that here. And we're going to look at the variations in those unit cells as a function of the doping in the sample. And so what you'll see here, this is the nu equals 0 state, the two bands, the empty band on the right, the filled band on the left. The nu equals 1 has a partially filled band, and on the right here, these two, and a completely filled band here on the left. Here's nu equals 2, again, filled band on the left, half filled bands on the right there. Nu equals 4 has the completely filled bands for both of them. And so what you'll notice is that the wave function is sort of centered in the unit cell in the nu equals 0 case. Here it's completely delocalized in this case. There's no strong peak anywhere in the completely filled band, but then in the partially filled band, the wave function is localized sort of at different spots in the unit cell. And so this is telling us something about the interactions in the system, whether you're sort of preferentially filling certain states or not. The other thing to look at is sort of the symmetries of this. So this is the topography image down here, which is a nice uniform spot centered on the AA. And what you'll notice is here, these are sort of oval shapes. This one and this one are perpendicular to each other, and they have major and minor axes, which don't match up at all with the sort of strain in our sample. So this is some other symmetry breaking coming into the sample. It may be it's a charge density wave type state that's forming or something of those type. And so these local density of states measurements allow us to gain access to the symmetries of the wave function and look at how those change as we change the doping in the sample. And you can see, obviously, the nu equals 0 and the nu equals 1 state have very different symmetries between them. Okay, so I think I probably should stop now, or should I continue beyond here? How am I doing on time?
We are happy to continue, but maybe we have a question, I think, from Alex.
I can't stop asking questions. So the local density of state measurements, they are it's literally a local probe. So is the bandwidth limited by the finite spatial extent that you're probing? Is there a sort of energy spatial uncertainty?
I don't think we're really limited by that. I mean, certainly, you know, the wave functions themselves have some sort of spatial extent to them, and that you know, that's what is sort of limiting. So we have the wave function of the tip, which is interacting with the wave function in the in this case the graphene, right? And so that you know, we're measuring that overlap really, and so that's what's limiting the sort of spatial resolution. But I don't think, yeah, I don't think it's anything beyond that. There's not a sort of uncertainty relation that's limiting our measurements.
So in other words, although it is a local density of states measurement, because you're measuring high density of states, in other words, I'm wondering about the width of the density of states peaks that you measure, right? And what the significance of that width is. And because it's a high density of states, essentially, are you saying it's delocalized? No, if it's a high density of states, it's highly localized. And therefore, are you only probing the local density of states rather than the density of states across a 10 nanometer by 10 nanometer area, for example?
Yeah, so like you know, we're measuring essentially the density of states is a function of energy. And so if we see a narrow peak in the density of states as a function of energy, that means we have a high density of states there. And so that means that the band should be flat in momentum space to give us this high density of states, which means that in real space, it should be a localized state. And so these measurements, right, then are showing that if the density of states is high, that's when things are very localized on the AA site. Right, so there is a sort of inverse relation there. The more localized on the AA site, so more localized in real space is more delocalized in momentum space, which means that the band is going to generally be flatter in momentum space, and that's what is the sort of thought of as a flat band in momentum space.
But as your peak gets sharper and sharper, the state that you're tunneling into essentially is, as you said, more and more localized. Hopping between that state and its neighbor in the next Moiré cell is weaker. And so your sensitivity to how flat those bands are is that, do you still have sensitivity to beyond a certain point, right? Or if that makes, you see what I mean?
Yeah, I mean, I think we're not in that regime. I mean, obviously if the band was, somehow infinitely flat and like a delta function, right, without any coupling to the next Moiré site, then everything would break down for being able to even do the measurements because, right, eventually the electron has to get from our tip to our contact some far distance away.
Right, right.
Okay. So we do have to have some kind of hopping or some kind of way of getting through the sample. And so, we're not reaching that regime where we're so localized that we can't still conduct through the sample.
Okay. All right. Thank you.
All right. So in this sort of last part, I just want to show that this is not something that's unique to graphene. If you can go to tungsten selenide, you can do a very similar type thing. And in fact, there's a whole range of materials that go beyond graphene that you can do this same kind of manipulation of the electronic states with. And so I want to just focus on tungsten selenide because it's interesting. It has an extra degree of freedom that you don't have in the graphene system. So in graphene, we had all carbon atoms in this hexagon. In tungsten selenide, because it's this 3-layer unit cell, we have a tungsten and 2 selenium atoms. When you create a bilayer, or stack 2 layers on top of each other, now there's 2 different ways to do this. There's the usual sort of Bernal stacking, AB, where you'd have a tungsten over a selenium, or you can have this AA stacking where you put the lattices directly on top of each other. So you'll notice there's essentially a 180-degree rotation here. This layer is the same, these 2 line up, this one is rotated 180 degrees. And so there's an extra degree of freedom using these materials that you don't have in the graphene. So the first thing, just a quick, if you are not familiar with tungsten diselenide, it is a semiconducting material. It has a band gap of about 2 electron volts. And so here's measurements of the density of states as a function of energy for a monolayer and a Bernal stacked bilayer. The bilayer has a slightly smaller energy gap, but they're both on the order of 2.1, 2.2 electron volts. And those states are centered basically at this K point in momentum space. Now, when you stack them on top of each other, as I just said, there's 2 different ways of doing it. There's this AA type stacking where they're directly on top of each other, or there's this AB where you rotate them 180 degrees from each other. So in these 2 cases, we have a 3-degree or 183-degree rotation. And when you do this, then there's a range of different high symmetry stacking configurations. In the yellow here, for example, you have the 2 lattices directly on top of each other, AA stacked. In the green, you have the tungsten above a selenium atom, or in the blue, you have the opposite. You have a selenium on top of a tungsten. And you can do the same kind of stacking in the 183-degree rotation, but there's 3 different sets in that case. And in both cases, when you do this, if you make a small twist angle, it will lead to a set of flat bands or relatively flat bands at the valence band edge. So before we had this parabola, this semiconducting, it has now become this relatively flat band at the valence band edge. And the width of this bandwidth, how much variation in energy it has with momentum, decreases as the twist angle approaches either 0 or 60 degrees, which is in my sort of definition here is 180 degrees. So the closer you get to 0 or 60 degrees, the smaller, the flatter the band gets. And so we've looked at actually what happens in both of these types of samples. You take topography, you see Moiré patterns. You get similar Moiré patterns for both 3 and 183 degree twist angles. And you have these bright spots here surrounded by dark spots. But the electronic properties are very different in these two materials, coming from the fact that we have this different stacking configurations in the two different materials. And so the first thing to do is to just look at these high symmetry sites here. What is the density of states at those different sites? And so I want to just focus on this figure in the bottom left corner here. This is looking at the valence band edge here. So to the right here would be the band gap. And at the different sites here, you see a whole series of different peaks that show up here. And they show up at different energies on the different sites. And if you go and look at this black curve here, that's the AA site. If we break it down a little bit more, we're getting contributions from different places in momentum space. So we're looking at this AA site, we're getting contributions from the two different K valleys, and there's also contribution from the gamma valleys here. So these different spots in momentum space give different contributions to the density of states, and you can break that down just by fitting these here with the different Lorentzians corresponding to the valence band maximum at K, the second valence band at K, the gamma maximum, and the second gamma. And so these are coming here. If you go to different sites, say there's tungsten on selenium, the ordering of the bands changes and you see a different spectrum, and you have to go and analyze these differently. But the interesting thing happens if you go and actually look spatially what's happening in these structures. So we're just going to move along this yellow line and take a density of states as a function of position along there. So the color scale is the density of states, white is high density of states, blue or black is low density of states. And you'll see there's these white spots showing up at certain locations in real space where the density of states is high. If we go and look at this in actually a two-dimensional local density of states measurement, in this 3-degree twist angle, what you'll see is the local density of states is high along the edges of this Moiré pattern in this hexagonal pattern. And this agrees with some calculations that were predicted for 3-degree twist angle, where they expect high density of states in red here along the outside of the hexagon that's forming the Moiré pattern. We can now compare this to what happens in the 183-degree case. So this is now just rotate 180 degrees from that, same exact measurements, and now you'll see there's only one spot where the density of states is high. It's just at this AB site at the corner of the unit cell here. And so this comes from the fact that we have this different symmetry coming from the different rotations and the fact that we have this 3-atom unit cell that gives then different variations in what the wave functions look like that are giving rise to these flat bands. In both cases, right, these are localized states, right? These are localized here, kind of like you saw in the twisted bilayer graphene, localized on one particular site. The other case was localized along the edge of the hexagon, a little bit more like what happens when you make very small twist angle graphene. And so these materials are, give you a extra knob to tune in the fact that you can use different 180-degree twist angles to modify the how the wave functions are how they're localized. The other advantage that you get using the TMD type materials for these types of measurements is that you can get these flat bands for a range of twist angles. There's not a magic angle. You know, these were 3 degrees, but they show up at 1 degree, 5 degrees, etc. And that means you can change the interaction between the different sites here. You can move them closer or further apart. And so that's what gives then rise to more tunability in these systems of TMDs, which we're just beginning to explore now. Beyond this, there's basically an infinite number of different systems that you can explore. You can combine graphene with, semiconductors, superconductors. We've done topological insulators, charge density waves, etc. So there's limitless possibilities, and that's just using graphene. If you start combining them with each other, superconductors with topological insulators, etc., there's a large phase space to explore. And so today I've tried to just tell you a little bit of what happens in these heterostructures when you play with the twist angle. What happens when you change the rotation between them, how that modifies electronic properties. But there's a lot of other things to explore. You can look at different materials, the different ordering of those materials. We've also looked at things like interlayer separation. What happens if you bring the materials either closer or further apart? How does that affect the electronic structure? And so really in these van der Waals heterostructures, there's a large range of different possibilities to explore where you can enable new physics to occur that doesn't happen in the individual layers, but only happens when you make these heterostructures. So I want to thank you guys for your attention, and thanks again for the invitation. But I also want to acknowledge and thank the people who really do the work, since that is definitely not me. It is all the members of my group over the last many years. So most of the work that I showed you was done by Chong here, who did the twisted bilayer graphene, the small twist angle work, and then Ziming, who did the magic angle twisted bilayer graphene with some help from Rachel, and also the tungsten diselenide work. And then Matt Yankowitz did the early graphene on HBN work. Those guys in red have moved on, and then the people in white are still members of my group. Had long-standing collaborations with many groups for things ranging from samples from Emmanuel and Pablo's groups to optics measurements with people at Arizona and the Japanese group providing us with high-quality HBN. And again, thank you for your attention. I'm happy to answer any other questions that you have.
Thank you for the great talk. So we enjoyed your fantastic results. Do we have any other questions? I think we have from Alex.
I couldn't let it go without one final question. So the nice work on the TMDs, I mean, beautiful talk. Thank you very much. The TMDs, with the bilayer graphene, you can essentially use the gates to cause a valley polarization, but you're limited. The interlayer coupling is really set by the stacking between the two layers and the tunneling between the two layers. Is the same story true with the TMD, that the interlayer coupling is essentially fixed by the fabrication, and that the gates really don't change that? You don't, or can you actually change the strength of the interlayer coupling with gates?
We can't really change interlayer coupling with gates. We have, so this image on the right is some work we did changing the interlayer coupling with pressure in the samples. So that's another external sort of knob that you can do to change that interlayer coupling. But you can't do it with something like a gate voltage, at least, maybe you can, but it's a very minor change.
Right. Because the overlap is too strong between the two layers, the tunneling is too strong between the two layers. Yeah,
I mean, it's just not sensitive to the gate. I mean, the gate just puts charge on the layers, but that doesn't modulate the tunneling between them in any sort of appreciable way.
Yeah. Okay. Thank you.
Yep.
Okay, I also have a question. So, in theoretical papers that ignore interactions and calculate the band structure of twisted bilayer graphene, you have two bands, flat bands, almost flat, that touch each other at direct chords at this brilliant zone of the Moiré pattern. Am I correct that so you always I haven't seen this Dirac Dirac nodes in the density of states. Instead, you always have interactions in use gap.
Yeah, I think that's correct. I mean, I think, the bands are, flat, that they're very sensitive to interactions, and we've always observed a gap opening, and not any kind of touching of the bands.
Okay, so
at the magic, for the magic angle ones. If you go away from the magic angle, then you do recover the Dirac cones.
Okay, thank you. Do we have any other questions?
So I have a question, Dimitri. Can you hear me?
Yeah.
Hi, Brian. Yeah, very nice talk.
Hi.
Thank you.
Thanks.
I have two questions. One is, I always have this question about the influence of the electric field that's there due to the STM bias. I mean, this field can be huge. Do you see any effect on STM set point on your features? You know what I mean? Like,
yeah, no, I got it. Yeah, so I don't want to skip back through the slides, but in the data here where we did spectroscopy on these topological states, right, we didn't see like a band gap until we applied a very large gate voltage, and that's because there's an electric field coming from the tip, right? So the tip is creating an electric field, and our gate is creating an electric field, and depending on the signs of everything, they either work with each other or against each other. And so we do need to take that into account in figuring out how much electric field is really being applied to the sample. And so that is a place that the electric field from the tip comes in. It doesn't depend on bias voltage too much, because as you change the bias voltage, the tip moves only by angstrom sort of level. And the electric field then isn't that sensitive to that. It's basically proportional to the separation between them. And so moving the tip up by an angstrom to change the tunnel current doesn't affect the electric field.
okay. And my second question is regarding the so bilayer graphene, especially when you had nu equals 1, 2, or 3.
Yep.
Wouldn't you expect some lift of spin degeneracy and some magnetism emerging? And is it?
Yeah, so when you have either 1 or 3, then you should have magnetism, because you should have unpaired spin in the system. Where unfortunately, our STM is not spin sensitive, so we're not able to directly measure whether the state is magnetic or not in our sort of tunneling measurements. Transport measurements have seen, these sort of spin states develop at the quarter filling of the bands.
I see, but let's say if you, at 4 Kelvin, if you had, let's say, some spin sensitivity with a magnetic tip, what would you expect for the exchange coupling, or would you expect to see some kind of magnetic contrast in spin resolved STM if you did have some spin sensitivity? Or
yeah, so since we don't have spin sensitivity, I haven't actually worked out the numbers to know if the coupling would be strong enough to observe it. I suspect it would be difficult. I think it's generally pretty small at 4 Kelvin. But as I said, I haven't worked out the numbers because we don't have spin resolved STM. I haven't seen anyone publish results on it. I know there are people out there with spin resolved STM looking at these kinds of things. So we'll see what comes of it.
Okay, yeah, thanks a lot. Very nice.
Okay, let's just thank the speaker again.
All right, thank you.